Hello, today's video is about length contraction with special relativity. I want to start by going with a brief review of the time dilation that we covered previously. So remember that we had a light clock and it emitted a bit of light that bounced off a mirror and then came back down to a sensor. So up, down, and it's just going bloop, bloop, and we can measure the actual time it takes for this to occur. And if we know the distance it travels, then we know the speed of light is going to be the distance over the time. Distance is 2d over the time. And now this was our proper time because the location is the same. We're changing in time but not location, so this is our proper time, t0. All right, now that was for an observer at rest with respect to the light clock. So we put this light clock into a spaceship, and now the spaceship is going zoom. What is an observer outside the spaceship going to see? So now I'm going to be the light clock in the ship, and you're going to be the observer. So as I'm moving, what happens to the path of the light as it goes up and then down? So it's going to get released, and then as I move, it goes mirror, and then back down. Not very symmetric, but hey. We can see that the distance, if we had originally had distance d from mirror to source, then now the distance traveled is a lot bigger. And so we know it's traveling at the speed of light, both in this situation and in this situation, because that's one of our postulates. So both traveling at the speed of light, this covers a lot more distance. It's going to need a lot more time. And so the observer who sees it moving says this takes a lot more time, whereas the person who's at rest with respect to the light clock says, oh, it was nice and short. And so the equation we had is that t is gamma t naught, where that's our proper time, and then this is the time for the observer. And we have to remember that gamma is always bigger than or equal to 1, which means that the time that the person outside the ship sees is much bigger than the time, the proper time, which is what the observer in the same location is going to see. So that was just what we had talked about in terms of time dilation. Now there's another interesting piece that we can talk about with special relativity, and that is length contraction. Time dilates, length contracts. What are we talking about here? So to do this, let's think about sending somebody on a ship from Earth off to our nearest star, Proxima Centauri. So Proxima Centauri, this is about 40 trillion kilometers away from us. That's kind of a long way. Even at the speed of light, it takes 4.24 years. So the distance here is 4.24 light years. All right, so we're going to send a ship over to Proxima Centauri. There's my fancy ship. And let's say the ship could move at 0.9 times the speed of light. Okay. So how long does it take the ship to reach Proxima Centauri from Earth in Earth's reference frame, stationary reference frame? Well, okay, if it took 4.24 years for light speed, then it's going to take 0.9 of that, and that's going to give us 3.82 years. So in Earth's time frame, that trip takes 3.82 years. But we know that for the person in the ship, it takes a lot less time. And how much time? Well, I just erased it. So we have t equals gamma t naught, where this is the proper time. This is the time for the person in the ship. And so Earth time is 3.82 years, and gamma, if you need a reminder, gamma is 1 over the square root of 1 minus v squared over c squared. So if we calculate it in this case, 2.29, and gamma is 2.29 t naught, So what do we get for T naught then? If you calculate it out, for a person in the rocket ship, it's 1.67 years. Not bad, huh? Takes light 4.24 years. Person in the rocket ship, year and 2/3. Not bad at all. So what's the issue here? Well, the issue is that the speed of light is the same in every reference frame, but speed is distance over time. So if we have the speed of light being the same, speed of light has to equal the speed of light, and speed is the distance traveled over the time. Okay, so that's the length of the trip over the time. We know these have to be the same for person on Earth and the person in the ship, but these times are different. So that means something is up with the distance, this length. And this is what we're talking about with length contraction. Now, let's say this is person for Earth and this is for the person in the spaceship. We had said earlier that the person in the spaceship has the proper time because that time clock, they're in the same location. So spaceship has T naught. Now we can talk about proper length as well. So when we have a proper length, L naught, that's going to be for the person who's in the stationary frame. So we want to be at rest to be able to measure the proper length of something. Just like when you want to measure the length of this marker, you don't want to measure it when it's at rest. You need to be holding still, measure both sides at once. So the Earth length is our proper length. All right. Yeah, different lengths, different times. So what can we do with this? Well, we know a relationship between time and proper time. That's right here. So let's go and put that in. L naught over time is gamma times proper time equals length over T naught. Well, look at that. Gone. And so I can have an equation that I can say length is length naught over gamma. Gamma is bigger than 1, which means the length that's observed by someone who actually sees the true proper length is smaller. The observed length of the moving thing actually shrinks. So that's what we have with length contraction or Lorentz contraction. And it just comes right out of the time dilation issue. So let's figure out what we have here. All right, got to erase. So if we have this relationship and we want to know what is the length of the trip, length in terms of the distance, what's the distance between Earth and Proxima Centauri for a person in the spaceship? We know it only takes them 1 2/3 years to travel. It must be a lot shorter then if we're going to make this work. So the length for the person in the rocket ship is the actual length, 4.24 light years, over gamma, which was 2.29. And if you calculate that, you get 1.85 light years. So a person on Earth sees this distance as 4.24 light years, about 40 trillion kilometers. A person flying at 9/10 the speed of light is going to say, well, that distance is a lot shorter. It was only 1.85 light years, which means it only takes me 1.67 years to get there. And so this is an example of length contraction. And we can kind of check that things are working out by saying, does the speed come out to be the same? If you want to say, I'm not sure about this. Is the speed actually the same? Does my math give me the same speed for both calculations? One on Earth and one in the spaceship. So let's give it a try. All right. Let's say Earth and spaceship. For Earth, the distance was 4.24 light years, and the time it took was 3.82 years. For the ship, 1.85 light years, and the time was 1.67 years. If you do the math on that, 1.11, 1.11. It's the same. So the speed is the same. These are consistent. And if you want to have some fun, try to figure out what this is in relationship to the 0.9c. See if you can figure that out. Now, something that's important for us to remember is that the length contraction only happens in the direction of motion. It doesn't matter if you're moving this way or that way. In the direction of motion is the only way that we care about for the length contraction. So if I have a three-dimensional object, like, real things are, if we have a three-dimensional object, then in two of those three dimensions, if we're moving along one of the axes, we are going to see no length contraction. Oof, this one's not cleaning up very well today. So what would this look like? Let's imagine a cube. All right, so we've got a cube, and I'm going to say that it's moving in this direction. So we have a velocity along this axis. For an observer looking at this moving cube, what would happen to that shape? Well, velocity is in this direction, so the up-down doesn't get contracted, the forward-back doesn't get contracted, but this direction right here, this part of the cube, will get smaller. And so what they would see is something like this, where it gets squished only in one dimension. And so that's just something to remember, that the length contraction only happens when you have something in the direction of motion. So there is a brief introduction. Let's now do a couple of practice problems. All right, so here is first problem to try. A rod lies parallel to the x-axis of reference frame S, moving along this axis at a speed of 0.630 c. Its rest length is 1.70 meters. What will be its measured length in frame S? So, for an observer in the rest frame, how long is this rod going to be? Well, let's start with a picture. It's always good to start with a picture when we're trying to solve a problem. And we are in the x direction. And let's see, rest length, that is its proper length, so that's our L naught, is 1.70 meters, and our speed is 0.630 c. What do we want to know? What will be its measured length in the moving frame? There we go. So this one should be pretty easy, yeah? We know that L is L naught over gamma. Well, let's figure out what gamma is. 1 over the square root of 1 minus 0.630 c over c, so 0.630 squared. And what do we get for gamma? 1.29, there it is. So, gamma is 1.29. The length is going to be our rest length, our proper length, 1.70 over 1.29. And we get an answer of 1.32 meters. Now don't forget, when we're solving problems, stop and say, does it make sense? I want to know what the length will be measured for the moving, what someone at rest will measure for the moving rod. Someone at rest will measure the moving rod to be shorter than its actual length. Is this shorter than its actual at rest length? Yes. And it seems like a reasonable number? Sure. So I think we've got that one down. Okay, second problem. A meter stick in frame S prime makes an angle of 30 degrees with the X prime axis. If that frame moves parallel to the x-axis of frame S with speed 0.90 c relative to frame S, what is the length of the stick as measured from S? Okay, so S prime is moving, S is holding still, and we have a meter stick making an angle of 30 degrees with the x-axis. Okay, so again, pictures are your friend for solving problems. So we have S, and we have S prime, which is parallel, And we have a meter stick in S prime. Okay. And it makes an angle of 30 degrees with X prime. So, we have a meter stick making a 30-degree angle with the positive x-axis. And let's see here, the frame moves parallel. Oops, so S prime is moving with speed 0.90 c, and let's just call it in that positive x direction. We want to know what is the length of the stick as measured from S. So we want to know what that is. All right. So in this case, S is not moving. S prime is moving. We want to find out the length of the meter stick as viewed from S prime. So oh, sorry, I misspoke. From S, from the stationary. So we're stationary. We are looking at a meter stick that's moving. That means things are contracted, but only contracted in the direction of motion. All right, so let's figure out what's going on here. We have a stick that is 1 meter long, and what would its components be? At 30 degrees, sine of 30, 0.5, cosine of 30, 0.866. All right, now this is the direction of motion. My 0.5, my height here, not contracted at all. It's perpendicular. This is the only side that's going to get contracted. So what is the length of this side going to seem like it? What does it look like it is? It's going to be smaller than 0.866, so 0.866 over gamma. Let's see, gamma is going to be 1 over the square root of 1 minus 0.9 squared. We did that before, 2.29. Whoop, hard to see. So 0.866 over 2.29. What is that length going to be? All right, I got it here somewhere. 0.378 meters. All right, this side of the meter stick, this component of the meter stick, effectively, gets measured not at 0.866, but we would measure it at 0.378. So the meter stick now would look like 0.5 tall, 0.378 in this direction. So, wow, it's no longer a meter stick, but it's going to be something smaller. 0.5 squared, 0.378 squared. Now, what's the answer here? I got 0.627 meters. Hopefully you're getting the same thing. So a meter stick at 30 degrees, 0.9, 9/10 the speed of light, actually looks like it's contracted to 63 centimeters. And the angle would change, of course, as well. Isn't that weird? The angle changes because only one direction gets squished. The up-down doesn't get squished, and so the angle would change as well. All right, so there is an example of a problem with length contraction in 2 dimensions. And then we had a simpler one, just calculating basic L naught L, and those should get you a good start on figuring out length contraction. Good job for watching.